Good morning. We've got people standing out back. There's lots of seats in here yet. If you want it, let's get everybody organized. I hate to do this to some of you, but I see there's a lot of scattered seats. If people kind of moved over a little bit, then we could get people seated here because we have several people in the back. I'm really glad to see you here. You know, when you are a speaker and you speak on a couple different days and so on, you always worry that on the first day and so on, everybody will be scared off and that, you know, come to the next day and won't see any audience. So I'm glad to see you here. I also see we have a dog in the audience, a guide dog, and actually that gives me a chance to talk about, I noticed on one of your brochures for your egg programs that there is a program through your continuing education. You've got a program on grandparents and kids. And our continuing education program at the University of Montana a couple years ago decided to start a program, a 2-day short course, usually in June, on a variety of things. They had astronomy and robotics and bees. And the idea is it's a grandparents and kids thing. To be a grandparent, you have to be over 50. To be a kid, you have to be somewhere between 8 and 12. They don't really check whether or not you're actually related or not. They just want an old person and an older person and a young person to show up together and so on. Well, the dean, I didn't know it, but the dean of continuing education was a little apprehensive about having a B course. You know, worried a little bit about liability, and she said she knew that we were all researchers, and you know, I don't teach as a regular basis, so you know, what did I know about dealing with grandparents and kids? Well, what you didn't know is we go into K-12 schools all the time, and my B manager is really, really excellent with kids. So day one went pretty well, and day two we had about 50% bigger class. Essentially, everybody went home that night and compared notes, and a whole bunch of people bailed on the class they were going to take and joined our class. But the real surprise was that there was a 14-year-old boy who was blind and somewhat mobility impaired, who showed up, unexpected. And he had had a bad day the day before. He had gone to a children's theater production, and the idea of the children's theater was that they could, he wanted to try out as a part for a speaking mirror. He figured he could do that. And all day long, they had the kids dance and do all kinds of things that he couldn't do, and at the end of the day, when the mother said, well, when are you going to get around to the auditions? They said, oh, we've already picked everybody. So he'd had a really bad day the day before, and so they talked to our folks, and because his sister and grandmother were in our class, and he joined the class. Now, I'm not sure he would have on his own joined a beekeeping class, but he did. And so I had the interesting scenario of a blind child, and how do you introduce them to bees? And fortunately, Scott's really good with the kids, and so I basically said, all right, we don't have that big a class. Scott, you take care of them. I'm going to work with the mother and the child. And that was one of the most fun days I've had in a long, long time. Now, I did come here with a little bit of pre-knowledge. I knew that there was a beekeeper in Montana, a commercial beekeeper, who went blind and continued to work his bees. And I also knew there was at least one researcher that worked on bees that was blind. So just because you're blind doesn't mean you can't work with bees. And the question was, how do we get the child to experience all those things? So when we pulled out a frame that had brood on it and so on, after Scott showed it to the crowd, I dusted off the last few bees. His mother took his hand and he felt everything. And then the mother did something that wouldn't have occurred to me. She asked him to go back and identify what he had felt. He got them all right. And then I picked up a drone, and it was buzzing, and I held it against his hand, and he giggled and thought it was pretty funny that he could feel that vibration and so on. And then I said, well, now this bee can't sting you, so if I let it loose, close your hand around it, so he could feel the bee walking around in his hand. And we just had a great time that day. End of the day, I said to him, oh, do you think you want to be a beekeeper? And he said, no. All right, well, I am glad to see you here this morning. I've had a great trip to Michigan. Roger, Dale, Dean, Zach made me really feel at home here, and all of you folks that I've met. I do have to bail this afternoon about 3 o'clock to get back home. I have to make 3 hops on the plane just to get here and back, so I won't get home until around midnight, but even chasing the sun. But I've had a good time here. I will be here probably until just a little bit after lunch. When we finish the presentation this morning, I will stay here to answer any questions you have. I'm glad to see some young people in the audience today because today we do what pays our bills. But you should be so lucky as to be able to do what I and my crew do for the things that really pay our way. Because we train bees. And I would not have guessed years ago that we could do what we do with bees, but we train bees. So I have a fairly good sized and very experienced crew. Robert Stecklin's I have 5 business partners and research partners, both the university and Beeler Technology. And Robert came to us, and he's a crackerjack programmer, and he uses things called artificial neural networks, which are computer programs that learn. So you throw them a data set, and they look at that, and you throw them another data set, and they look at that, and pretty soon the computer starts figuring out patterns and working through things. We'll show you some of Robert's work a little later. Colin Henderson teaches in the nursing program, but he was originally trained as a mammologist, but he's a quantitative ecologist, which means he does all of our experimental designs and all our statistical work. David Firth is a business professor. He figures that scientists are scientists and don't know much about business, so in terms of trying to make the company a success, David is an equity partner. Steve Rice is a 14-year chair of the electronics department. So you're going to see a lot of whiz-bang electronics today, and that's a lot of that is Steve and his associate who started teaching with him but now has been lured off by the Federal Forest Service, Ted Etter. He does all the designs for our circuits. Stott Debnan is our bee manager. He came to us as a student. He's a bodybuilder, and I'm sure most of you understand that having a bodybuilder on the crew moving beehives around is a good thing. But he's also superb with bees and children, and Scott is the self-proclaimed bee whisperer. But some of the things he gets bees to do and so on, I might actually believe he's a bee whisperer. He takes mean bees and makes them docile. Phil Welch has been with us a long time, Josh Rice, Sarah Red Laird, and Will, all our electronics or technicians or former students. And in the summer times, we generally pick up about a half a dozen students to flesh out our, build our crews and so on. We do accept volunteers. We have had some interesting volunteers over the years. But what I'm going to talk about today is training of bees. Now, I started my career using bees to bring home and survey areas for pollutants. And we did a lot of EPA Superfund sites, et cetera. And the issue is, as you all know, bees go out and collect everything, and they bring it all back to the hive, and then you can sample the bee at the hive or the things they bring back, and you can pretty well tell if there's something of interest or concern out there just by the bee bringing it to you, whether it's chemical or biological. And then the next step was the Army got a hold of me one day and said, we got a bunch of hazardous waste sites in Edgewood, Maryland. We're not exactly sure what's buried in some of them. We're afraid if we breach one of those barrels, we might release something toxic. Do you think you could use these bees like a canary to see if it had an adverse effect and give us a warning? And so we built, in 1995, the world's first electronic beehives that had counters on them and so on. And Robert, with his magic neural networks, built software programs. So if the bees didn't come home on a day, they went out the door but didn't come back, we would know sitting in Montana whether that was because it was raining or because there was a toxic breach and so on. And really shook up the contractors because they saw the guys that were doing the mitigation and they were capping these toxic waste sites. They were 16 miles from Baltimore, and all of a sudden we ring these sites with beehives. And I remember one of the contractors looking at me and he said, I suppose this means if we kill the bees, we're in trouble. And I said, And the whole idea was that maybe if the bees were sacrificed, if the bees went first, you could have a chance to get an alarm down to Baltimore and so on. Well, then pretty soon a guy from DARPA shows up and says, well, if you can get bees to collect all these things, and some of these things are harmful to bees and have an adverse effect on the bees, can you get the bees to show you where they found the stuff that's of a problem? And I did what I always do. I said yes. It scares the heck out of all my colleagues, but I never say no if I think there's any chance at all we can do it. So I said yes. There were other people that they actually had approached earlier, and other insect specialists and so on, and most of them said no. So I said yes, and I was the first one that said yes. So that was in about 2000. And basically at this point in time, we know that if it has an odor, we can train a bee to find it, just like a dog can be trained to find drugs and explosives and dead bodies and so on. And we can find almost all those same things using a honeybee. So we train bees to find the sense of things that we're interested in. Now, bees can be trained to odor, but they can also be trained to vision. They see quite well, thank you. Maybe not the fine detail that you and I see, but they see shapes and they see colors very well. They don't see in the red zone very well, but they see in the ultraviolet. So you and I don't see it in the ultraviolet at all. And I've had people at times say, well, if bees can't see in the red colors and so on, they must not be very good in their vision. And I think if you could ask a bee, the bee would tell you that all the flowers have ultraviolet patterns on them and so on, and the bee would say, you got a pretty lousy vision because you really can't see where the target, the goal is, where the good stuff's at, because those flowers have lines and circles and other things pointing right at the nectar sources and so on. So bee uses that and so on. So bee probably think we're not very good. And those big wraparound eyes, well, you can see all the way around and so on. So you don't just see ahead, you see on the side and so on. So bee would probably think that's a pretty good idea too. So you can train bees on color, you can train bees on shapes, and there are researchers in Australia that claim that bees can be trained to recognize faces by photographs and so on. Now we know they can recognize people. You may wonder or think about whether bees can recognize you, or I have had people say bees recognize them. We know bees recognize people because we train bees, and when we train them, we use a reward system. And initially, we used to go out and manually fill up little syrup feeders and so on. We had to quit that because the bees very quickly figured out who the feeders were and the vehicles they drove. So bees can recognize odors, and they can recognize visual clues. And if you're Srinivasan, an Australian researcher who looks at how bees experience the world and view the world by their sight, and then applies those principles to robotics, airplanes, and other self-propelled things. No pilot, these are all robotically controlled things. He uses the principles that he derives from bee vision to build a very simple guidance system for his robots. And Srini has done a lot of work flying bees through mazes. And Srini has actually managed to combine both vision and olfaction. So in a maze, if the bee flies into the first box in one of Srini's experiments, and it smells lemon, he's trained it to follow yellow dots. But if in the first box it smells lavender, he's trained it to follow the purple dots. So the bee flies into the first box, takes the bee equivalent of a sniff, and then decides where it needs to go. So Zach yesterday made some comment in his workshop about bees falling in the feeders and drowning and said the bees are dumb. Zach, bees are not dumb. Lousy swimmers, but not dumb. So I'm going to show you a short little video. Now the guys out here want to sell me your logo wear for MSU, and my degree is from MSU, Montana State University. And for 38 years, I worked at the University of Montana. And although our two campuses have about 15,000 each and rather small compared to yours, we are NCAA national champs twice in the last decade at U of M. And for 17 of the last 19 years, MSU has been the loser. And we take our football seriously. So, a couple years ago, the Montana beekeepers were meeting in Missoula on the same weekend as the big MSU U of M game. And regardless of how we're standing nationally, the U of M, the MSU game is the game to be at. They fill the stadiums and so on. Well, the Bozeman folks are the Bobcats. And at U of M, we're the Grizzlies. And so we repeated Srini's little maze issue with colored dots, only my students didn't want to use colored dots. We trained our bees to be loyal to the Grizz. They don't want anything to do with the Bobcat. And I'm sure by now you're thinking this, because the giggle factor is big in this. But tell me whether you're still giggling by the time we finish this morning. All right. So, I think it's time you saw our bees. There's the Grizz logo. And there's that blankety-blank Bobcat logo. Can we take that light down? Whatever. Yeah, get it up here. Darken it down. So yeah. Thank you. I'll have another video. The videos with the bees on are hard to see if you got them. How cool is that? Can you train a bee? Now you know what you need to do for your science fair project.
Do you have that video on YouTube by any chance?
Yes. It is on YouTube. All right. So, why is the military interested in training bees? Because they want to find things rapidly over large areas at no risk to the handler. Landmines, for example. Gold standard to dogs. Dogs are great. One problem. Two problems, actually. One is the dog works at the end of a 25-foot leash. You can't just let this dog wander over the field. Secondly, it's trained to sit down when it smells what it's looking for. You really want to be sure that that dog has worked from the safe area in and is not sitting on the wrong thing. And unfortunately, every so often, dog and trainer disappear. Nice thing about bees, they're not going to set anything off. So instead of yards or 25 feet, as you all know, bees can fly a mile or two easy. And a few hundred yards is no problem. They're quick to train. Takes quite a while. I saw the dog here for the blind. Where is the dog anyway? Yeah. How long does it take you to train that dog?
The puppy raisers have them for a year, and then they go through intense training for 6 months after that.
A year and then 6 months. 24 to 48 hours, we got our bees trained. They learn their initial lessons in a half hour to 2 hours. So we got very rapid turnaround. Once we train them on one thing, we can switch them to another in 30 minutes. The other thing about it, dogs, like us, have bad days. Just don't feel like working that day. Got a cold in the nose. Bees are driven. If they can fly, they're out doing their thing. They're not distracted. They like hot weather. A lot of scenarios, dogs and handlers have to be limited to about 20 minutes because out in the deserts and so on, it's just too hot and both need to cool down. Bees thrive on it being good and hot. We've flown about 119 degrees in Yuma and so on. So what we're training on are vapors, whether it's a decomposing body, a drug lab, the solvents that the labs use, landmines that leak explosives. We're training them on the odors from the sources. We have safe standoff because we don't put them on a leash, and I will show you how we do that. We use lasers to find the bees. So we train the bees to find things, and then we use lasers to find the bees. I don't know about you, but I don't want to go tripping across the landmine field looking for where the bees are at. So we had to come up with a safe way of finding the bees. So we train the bees. The bees are trained like a dog. They don't sit, but they essentially repeatedly come back to the source when they find the odor they're trained to look for. Then the challenge for us is how do we find the bees? And we use lasers to do that. So we're not on a short leash. We can stand off at a safe distance. they're really cheap compared to dogs. By the time the trainer trains them for a year and another 6 months, the original purchase price and so on, the dogs used in the dog teams, the handler and dogs for demining, they figure it's about $100K a year and so on. So bees are quite cheap by comparison. And we have set this up so we can use any bee in any type of hive anywhere in the world. So we don't have any type of special bee here. Your garden variety honeybee does the job quite well. And they have really high sensitivity. Now, when we started this, people said, well, no sense in looking at bees because, after all, bees don't have a very good sense of smell. That's a fiction. They've got a great sense of smell. And the fiction was also that they can smell a few floral scents and some pheromones. And that's not true either. We have yet to exhaust all the things that we have found that they can detect. So their olfactory system is very, very good and very broadly based. We don't know whether they're better than a dog or not because both the bees and the dogs, their odor detection sensors are better than any instrument that we have. We have to pump an air sample onto a cartridge that has absorbent material in it for a half hour just to get the sample concentrated enough so that when they heat it up and push it off into an instrument, a benchtop instrument, we can detect some of these odors that the bees are picking up instantaneously. So we don't have any instruments that are as good as either the dog or the bee. So it's impossible to compare the bee to the dog other than just kind of general, put them both out in the same field and see what they find. And we've done that, and they look like they're working pretty well on the same level and so on. We don't have instruments as good as they are. So they can detect odors of explosives, for example. And people originally said, why would they be able to smell explosives? Well, they can. At odors of parts per trillion. And on a test minefield in 2003, using the air pumps and pulling samples, we found that this high above the buried mine that had been buried for several years, we had 5 to 10 parts per trillion of the explosive vapors. But I'm going to show you a video in a moment that shows bees at tens of yards out falling in the plume from that, which means since that plume disperses and spreads out, that's 40, 50, 60 feet away, that plume's down in the parts per quadrillion. We have no instruments of any type that go to those kind of levels and so on. So I don't know about you, but I have a hard time dealing with a million, much less a billion or a trillion or quadrillion. But there's a fun little website out there called the Megapenny site. And the Megapenny site uses a penny to illustrate these large numbers. So, if you haven't, go look up the Megapenny site. How much is a million? Well, there's our penny. We all know how big a penny is. If we stack up the penny, a million pennies, and you stand beside it, that's what a million pennies would look like. That's a pretty fair-sized pile of pennies. There's a billion pennies. There's a billion pennies on a football field. And you also will notice that we still have our little guy there, standing there by his billion pennies, or 10 billion pennies in this case, 10 billion, excuse me. So that's 10 billion pennies. Now remember, the plumes from these landmines are typically in the order of low parts per trillion. So let's see what a part per trillion looks like. Somewhere on there. Oh, there he is. See the arrow? There's our guy. He's over here. That's a part per trillion. 5 pennies in that pile. And the bees can smell it. But remember, that's this far above the buried mine. 50 feet away, the bees picked it up. That's a part per quadrillion. There we go. somewhere the little guy is there. He got kind of lost. That's where the bees are working. Throw a few pennies into that pile, and that's what they can pick up in terms of the concentration of the odor. That's pretty small, isn't it? Think you can do that? All right. That's sensitivity. How accurate are they? Now, I'm going to walk you through this. This is a little technical. Yesterday, people said I threw some big words at you, and unfortunately, sometimes there just aren't simple words for things. I'll try to make this simple. If you use radar, and you want to know how good that radar is, one approach that is used, a mathematical approach, is something called the receiver operating characteristic, or curve. Now, what's going on here is that on the vertical axis, where it says true positive rate of 0 to 1, and the bottom axis going from left to right, 0 to 1. You score your sensor on this chart. And I'm going to walk away from the mic, but I'm sure my voice carries. All right, so if we fall on this line, there's really the chance of false hits versus real hits is equal. So if your sensor is this good, it's worthless. A good radar system looks like this. That's a good radar system. A perfect system is up here in the corner. If it squared the corner off, it's perfect. So the closer to the left-hand corner it gets, the better the sensor. The closer it gets down here, the worse it is. Anybody want to guess how a bee stacks up on this? Now, it's a little hard to see that. So I'm going to show you another chart, but the other chart is up in that corner. Here we go. Not 0, 0.9988 to 1. At part per billion concentrations, say a dead body, we're following the red line. How close is that to perfect? And at parts per trillion, this is 0.9998. Now, for 2 years, we had an Army group of signal processors, all mathematicians, that DARPA hired to keep us honest. They said, well, we really want you to train bees to find these things, but we don't trust you. They didn't say it exactly that way, but that was the message. And the head of the signal processing team basically came in and said, I don't think this works. He says, I think the government has wasted a lot of money. I'm going to prove that these bees aren't very good. He thought we had some type of scam or fraud. For 2 years, we set up bees. An independent group videotaped them. We did as much as 36 days continuous trials. All the videotaping and stuff was done independent. All the targets were blind to us. All we did is train the bees. And 2 years later, after they had sliced, diced, and manipulated that data every way they could think of, they walked in and said, every way we look at it, the bees are performing. They're doing exactly what you said they do. Let's hear for the bees. And I said to this guy, good, now that you believe the bees can do it, you've been telling me for years that the generals and others understand these rock curves. That's a very common way for them to assess performance. I said, can you do a rock curve? Oh, yeah, that'll be easy. So he went home that afternoon, and we had a consultant that was trying to work with, that was an ex-military guy that was assigned to us to help with some of the technology issues on this. At about midnight that night, the consultant got a call from the mathematician. He said, I just did the rock curve. That's the curve he did. He said, it's incredible. He said, I've never seen a center like that. So, are they any good? Are they accurate? You betcha. So, I'm going to do a 7-minute video here. I've got one videographer here. If anybody here is snuck in a camera on me and so on, please do not video this next section. There are sensitive issues here. My concern is I don't want to see this on YouTube, and I don't want to see this on the evening news and so on. It could cost me $1 million if that happens. So I don't want to see this. But if I think you ought to see it. In 2003, we went to a test minefield that the Army, at that time DARPA, had at Fort Leonard Wood, Missouri. And we rented a laser because we thought that the way that you might be able to find bees was using a laser. And we used a laser that had been designed to count fish from an airplane. The airplane flew over lakes. The laser was a green laser aimed downward, and it could pick up schools of fish. Laser beam, like my pointer, goes out, bounces, and when I point that pointer at that beam from that pointer is coming back to me. If I had a telescope mounted on my little pointer here, the telescope could pick up the laser beam as it bounces back. And when you bounce off the fish, you get the return and you can find where the fish are at. So, well, we do the same type of thing here with the bees. So, what you're going to see at that time, in 2003, we had big, clunky, pressurized Coke cans for syrup. We had a lot of spaghetti tubing around that were networking all the feeders we were using. And we rented from NOAA this fish-finding laser, and it pivots on a cam. Well, it was jerry-rigged just before it. And the whole thing fills up a 14-foot trailer. It's a roughly a $500,000 laser. It cost me $20,000 just to rent the silly thing for a week, and it worked. It took a student another year to get the software worked out to essentially, because they'd never had a moving laser before other than in the linear straight line movement in the plane. But this is a 6-minute video. The things I want you to get out of this. One is, you'll get an idea how we train the bees. Second is, you will see the bees following my colleague carrying a tray with a little bit of dinitrile-toluene, which is a breakdown product of TNT, out into the field with the bees following him like the Pied Piper. Watch how that bee flies. They oscillate back and forth across the vapor plume because they're comparing the strength of the odor from left antenna to the right antenna and adjusting as they go. You'll see a big green beam sweeping the field. That's the laser. It was that powerful and that bright. Mid-afternoon, you can see that thing sweep that field. This is a real minefield. They have removed the fuses, so you can walk across it. They suggest you not jump on the field, but you can walk across it. And the field has, on a grid, areas that have no mines. Any grid intersection might be no mine, an anti-personnel mine, which isn't much bigger than this, an anti-tank mine that's about the size of a good dinner plate, big dinner plate, or a box of cardboard boxes waxed with TNT in it. So this is a blind trial. We don't know at any intersection, and you'll see little flags out there marking the intersections, what's under any one of them. But this was when we got done, they gave us a report card and how well we did. You will also see a bee fly up to a bottle of dinitrile-toluene and appear to be reading the label. That bee was actually a quarter mile from the test site. We had a little air-conditioned shed, and we kept the training material there, and we had the video crew with us. And the video crew got hot and went back to the shed, and there was a little picnic table sitting out. And they didn't ask us about this, but they had seen us pouring the DNT out into a tray. And they got curious, so they set the bottle out on the table and cracked the cap on it just slightly. And a quarter mile from where we were doing the test, they immediately had a bee show up, picking up that plume and checking it out. And I'll swear, she looks like she's reading the label. So, sit back, and I think for this one, if we can pull all the lights down so that you can really see what's going on. So if we can darken the room, we got the front. Can we bring the room lights down just a little more? I want to really be able to see this video. For those of you standing in the back, there's still some seats here. If I could stop for a moment here if you want to come in and sit down. All right. Well, when we first did that, we knew we couldn't get a laser map back right away because we had the laser, but we didn't have any software to process the data we collected. It took a student working at MSU a year to process that data. In the meantime, Colin and I, and Colin was the guy you see walking around with the bees following him, he's my research partner, we could walk that site, and so we walked the site and stopped at each of the pins and counted bees. And when we did that, we ended up with this map here of where bees are at on this minefield. That map, the brighter the color, the more bees we had. And you can see that there's lots of bees over here, there's some bees here, there are fewer bees here. What we're seeing is the differences between the anti-tank mines, the anti-personnel mines. We found 95% of everything known to be buried on that field. But more importantly, we found 100% of everything known to leak explosives. As these mines age, they crack and leak and the seals dry out, but they don't all leak right away. And so, to the best of our knowledge, we found everything that was on that field that was leaking. We also found between the laser and the field, and that field's about the size of a football field, and that laser was about a football field back, that the guy running the laser in that trailer said, when you have the chemist come in and do some validation chemistry sampling, have him sample this point here, and he took his foot and he drew an X on the ground. He says, every time we do this, he said, there are bees on that spot. We found something that nobody knew about. That impressed the military quite a bit. And so, well, a year later, when the student finally got done with their project, we generated the same map. This one is visually counting bees, but remember, we walk safely on this field. You can't do that in most mining fields. This is a laser-generated map. It shows a little wider area because you can see where our feeders were off to the side. But basically, these two maps are completely congruent, and some of the issue in between, don't worry about too much, but that's just some of the chemical validation. These reports are available online. You can actually read them. Yes, sir?
Does the new mine fields have leakage as well?
The newer ones are tougher. They all start to leak pretty quick. But, you know, if they're freshly buried and then the soils are all disturbed, it's hard for the bee to find a specific signal. This works better on an aged field and so on. If you were to, you know, so you have to take some of those characteristics in place. But this, you know, there are 80-some countries that have mined areas. The RAND Corporation assumes it will estimates, using the best available technologies, it will take 500 years to clear known fields, assuming nobody buries anything else. The UN also anticipates that bees versus dogs, that the bees could speed up the process by 10 to 15 fold. So maybe we can take that 500 years down to 50. And why am I concerned about it? Every year, 20,000 or so people are maimed or killed by these things. If you could take and cut 450 years of risk out of that equation, that would be really something, okay? So, as you might notice, I'm not the youngest guy in the room. I would like to see this happen before I either retire or pass on. So, this is really where we're at. This is our what we've been doing for almost a decade. We are getting better and better and better at training, and our equipment is getting better. Biggest problem was that laser was too big, too expensive, and too cumbersome, moving a 14-foot trailer around and so. It also was not eye safe. You notice that Joe in one scene by that stake was wearing goggles. So we can go a mile and see bees at a mile. We have lasers we've actually had to detune so it didn't incinerate the bees on the wing. And so, problem is those aren't practical for most field work, and they're too expensive. But the Geneva folks with the landmines and the dogs say a 100-yard standoff would be a good idea. So we aim at about 100 yards because we can detune the lasers and cut down the power of them enough to make them reasonably eye safe at 100 yards. So, yes, sir?
It's reasonable to assume that when the enemy puts landmines down, there's got to be a sense of some
Yeah, so you asked if you bury a mine in a scent of some sort, and it absolutely is. And if you know what that scent is, or can identify that scent, or make a reasonable guess at it, we can train on it, and so on. So, yes.
After the bee has been trained to and is rewarded for finding a scent in a controlled group, how is that a bee then later removed? What is their reward later when you don't know where you're going to find?
Questions about training and rewards and so on. All right. That's what this particular picture is about. Nice lead-in. Thank you. All right. You can train a bee. Lots of people have trained bees. Von Frisch trained bees to go to rewards. You know, the feeder that had a color or scent would have the reward, and the one that didn't, you know, no use wasting your time on that. The problems, as I said, are that they identify the people filling up the feeders. And if we feed too much, they get lazy and just go to the feeders. And if the feeders are off for too long, they basically figure, like Mother Nature, the flower has stopped yielding any reward, and let's go on to the next thing. They have, you know, they have a very short attention span on these type of things. What our patents are on and our trade secrets is how we train these bees. I will tell you, it is a food using a proprietary solution-based reward system. With the dogs, you train them on play, right? You know, Fido at home, you might feed kibbles, but you know, working dog, if you feed them on food, they get fat. You want those dogs in good health, so they train working dogs, the demining dogs, the drug-sniffing dogs, etc. They're trained on play. You know, I haven't found a bee yet that cares anything about play. But food, yes, sir.
If you move a beehive maybe 10, 15 feet away, the bees will return to the old position of the hive, not to the new position of the hive. Shouldn't they be able to smell where the new position is?
Well, they should be able to, if you move a hive, shouldn't they be able to smell it? Now they could probably smell it, but then that gets into the fact that do they really recognize their hive as much as the books would have us believe they recognize their hives? I have some questions about that, but the primary scent has moved over the other, and so you would think they ought to follow the hive. They seem to have a building compass type of thing. We've done this on lawns and stuff, and you move in a short distance, and if there's no other landmarks around, they get lost quicker than, as you say, they're easily lost. What we can tell you on this is that this system that we have works because we train them to search by odor. And if you know Adrian Winter, you know that's his favorite hypothesis. Whether the dance language figures in on this or not, I don't think it's needed because at the short distances our feeder is away from the hives, bee flies out the door to see the feeder and so on. So even the most, you know, so it's, you know, in the dance should tell them to go to the feeders, not to do any searching, because there's no reward out where we get them to search. But it's an interesting dance that we do with these feeders. And so you saw that video, those big pressurized feeder systems and so on. Clumsy, difficult. This is our feeder system now. It's about the size of a notebook tablet, you know, 8.5 by 11 roughly. Solar powered, microprocessor controlled with communications. And these feeders talk to each other and talk to a netbook that we have, and we can orchestrate those feeders and what they do and put them on autopilot or semi-pilot or talk to each other or be manually overridden, any combination that we want. So we can play the feeders and watch with the lasers where the bees are going and then retune that as we go. When we train these bees, as soon as we get a few bees trained, then the self-recruiting starts to kick in and so on. And as long as we keep these things charged up and with the feeders, with the bladders full of the food reward, we can keep them going day after day after day after day. They become a self-training system. We don't do anything. So when we did a test in August last year, I had a trailer, but this time the trailer had 8 colonies plumbed into it, stacked up on the inside, with the excess to the outside and just a slide to keep them in. It was air conditioned. Down, it was a 12-foot cargo trailer. Down the middle was enough area that we could store the laser, and up in front were all the feeders. We pulled in on a Sunday morning at 8 o'clock after 2.5 days on the road from Montana. We pulled in, unhooked the trailer, dropped these feeders on the ground, and 30 minutes later said to the guys, okay, we're tired. We've been driving for 2.5 days. We'll see you tomorrow. That's where we're at with the system. And on Monday, we showed up, fired up the laser, and went to work. So that's our feeder system as it exists today. But sometimes we want bees to search that field and not that field. And we don't want to move those colonies around from just what you said about them getting lost. So once we bring into an area we want to survey, we want to set those colonies down and leave them there, or leave them in the trailer, whatever. And so basically what we do is we have this robot. So the robot plays like the Pied Piper, and it essentially leads the bees over to the area we want them to search. And so if it's a hazardous area or someplace we want to do it covertly, you know, we want to check out what somebody's doing and so on, we just let this do the job and so on. Got a GPS on it. GPS there. There's our feeder. There's our scent pop-up. Pops up, releases scent, pops down, scent disappears. Camera so we can see where it's going. Robotic feeders. And you should see them when they're feeding on this thing, and it moves. You would think they might let loose, but they hang on for dear life. You saw that laser, how big it was in that big trailer? This is what our laser looks like now. That's the laser. And a portable computer. We can roll that onto a plane. And I just let a bid to refine that one more step. So that system works, but it tends to get out of alignment a little bit too easily, so they're ruggedizing a little bit, making the alignment. But by mid-April, I'll have an upgrade on that, and by the 1st of June, this system is going to be ready to rock and roll. And our objective this summer is to fully calibrate this system on real minefields and do demonstrations from the United Nations and the military and law enforcement and others about what we can do, because the goal here is not, we really haven't done anything since 2003 that's substantially different from what you saw in that video. What we've done is refine the systems, refine the equipment, made it all so that it's basically throw a switch and it works, and we can walk away from it, and so on. And that's where it had to be. Because even with dogs, people are a little reluctant to trust dogs and to deal with dogs. Imagine getting past the barrier of the giggle factor and telling them that you got a system that you can use bees to do this. And we had to have a system that is not, well, if you're trained for 6 months and so, train the bees in a few hours. We need to be able to train the people in short periods too. So this system has to be really easy to use in almost any setting, and we've had lots of inquiries about different uses. But what's been holding us back is that laser. We have had to get a small, portable, affordable, reliable, turn the switch on and it runs and maps, and we are now there. I didn't know we were going to get there, but it's there now. It's been 7 years in the making. So that's the whiz-bang stuff, but there are spin-offs to this. For example, that laser is of great interest to a lot of the seed companies, because with shortages of bees for pollination, and if you don't have enough bees, the value for each hive goes up. Now, as beekeepers, maybe you like to see that, but the growers don't necessarily like to be hostage to really high rental prices, and in some cases, they just can't get as many colonies as they'd like. And if you talk to a grower or a beekeeper, everybody's got a different opinion of how many colonies you need and what kind of array around the field. How many, should you have them singly or in groups? Should you have them through the field, on the sides of the fields? Should they be upwind or downwind? Nobody really knows the answer to that. There have been a few simple studies where a bunch of students out there with click counters counted bees, but other than that, there's really then no way to determine how bees explore new areas. Well, we can do that now because we can map these bees across the space. Those lasers sweep 180 back and forth. We can set on the edge of the field and sweep that field. And we can put those colonies down in different configurations. our lasers, that big laser, only knew that it was seeing small moving things. Part of what's taken us 7 years is that our lasers now can pick a bee out from a fly. The way it works is that the signal it's looking for, everything bounces the signal back, but it ignores all the data except for one thing. It is looking for a signal that comes back at the frequency that the wings of a honeybee beat at. And it ignores everything else. And when it sweeps this way and that, the angle it hits, there's a bee, there's a bee, there's a bee. That's fairly simple. Guess how we tell how far away that bee is? Pardon? Time. You got it. Light moves around 1 foot per nanosecond. So we time the signal out and back. And we pulse the laser. But the laser is pulsed at fractions of a nanosecond. The faster we pulse it, the closer we can get to where that bee actually is. And so our friends at Montana State University, our sister institution, did the laser development for us. At U of M, we do all the other technologies. And a Native American-owned firm called S&K Electronics has built the commercial version. So like that simplified feeder that's actually more or less a throwaway system. If you have to abandon it because you can't recover it or you're in a hurry or so on, it's cheap enough that it essentially can be thrown out, and if you have to discard it, you haven't lost a lot, and so on. So those are our partners that have been working very, very hard on this for the last 7 years. So we could, we've also run into the growers that say, well, they use, for example, leafcutter bees on canola for their hybrids because they don't want that gene pool spread down the road, and honeybees forage too far, but the idea is that leafcutters don't fly very far. Well, they don't know for sure. They can use this laser again to find out, and so on. Then there was a notion that there's a paper out of North Dakota that said, on sunflowers, if you combine honeybees and bumblebees together, both of them became better pollinators because they apparently compete with each other for the resource. And so the canola growers up in Canada said, well, then it must be that if we mix leafcutter bees and honeybees that we get the same phenomenon happening. Who knows? So then their question was, can you laser look at 2 different insects? Well, actually we can, because the laser gets all the data back. And then we just, through the software, pick out what we're looking for. So yeah, that's possible. We can do a dual thing. Want to find mosquitoes and Nile virus? You can do it with this laser. And so, not the Nile virus, but the mosquitoes and so on. So these lasers may have some real uses in agriculture and so on, beyond the fact that we build them so that we didn't have to walk across the minefield. Or sneak up on the house with drug dealers in. All right. So I'm going to tell you about a little bit of the other things we do. Hopefully by now we've impressed you that honeybees are much, much more capable than you ever imagined. And for all the young folks here in the audience, young in age or young in spirit, I challenge you to take up training bees. And see what you can get a bee to do. Think you can get the bees to do what we do? Well, you know where to come if you need to be trained. All right, so one of the problems with somebody like the military using this is they say, well, we'll need the soldiers to run it. And what do they know about bees? So and then there's the question of what if the bad guy wants to put the system out of commission? Interfere with it, poison the bees or something. So there's a parallel effort here, and that is to make beekeeping so simple that you don't have to open the box. And there's probably a use for that, not so much for you folks that love your bees and have a couple colonies out the back door, but I come from a state with a couple 100,000 colonies, more or less all owned and run by about 60 people. Montana is predominantly commercial, predominantly migratory, and a small operation in Montana is 2,500 colonies, and a medium-sized one is 5,000 to 10,000 colonies, and then we have a few bigger ones. And they may be in 5 different states all at the same time, and they spend a lot of money sending crews out to work those colonies hundreds of miles on a run, and inspecting them. And then when they get to things like medication and so on, it's generally a decision of, well, gosh, we took a look, we saw a couple things, we better medicate everything because we just don't have the time to look at all of those colonies. Or they look pretty good, we won't medicate anything. Not good for management. And if you medicate everything, not only do you increase the risk of resistance setting up, but it's going to cost you a lot and so on. So, show you a couple other things we're doing. We're going to talk about using infrared to look at a bee population from the outside of a colony, an acoustic scanner to diagnose the presence of disease and pests, and smart hives or pallets that tell you how your bees are doing from 100 or 1,000 miles away. So the first of them, and again this is available on the internet, same folks down in Bozeman that did the laser also did a bunch of optical subtraction systems, and in this case we're using infrared cameras. What's unique here is some of you may have access to infrared cameras, is that we use a calibration system so that we can clearly and very accurately get very subtle changes in temperature and interpret that data. Can we get the lights down, please? So this is a calibration system. This is a little heater box that is very, very precisely controlled. It costs as much as a camera. That box is $20K, 20,000. And so that's what you'd be missing. These are colonies that I had in my bee yard just sitting on stands. We have a skunk problem because we're by the river, so we put them up in sawhorses. And this was an August scenario in the early morning. And one thing you can see, notice the heat coming out of the entrance of the hives, and you can see differences in terms of the where the bees are at, how high they are, and this one the cluster is split, and their general orientation. And you can also see a couple colonies that aren't showing much of a heat signature. This one's is not laying anymore from the queen, so there's no brood, and so they're not thermoregulating, but there are bees in it. You can see the bees, and this one's a dead out. This is a little bit more. This is midsummer when you can really see the differences in them. And you see these colonies, the picture at the top, the colonies, and here's the same one in infrared. Look where those colonies are at, how those bees are distributed, see the heat signatures, and so on. So if you're the soldier using these colonies for a canary or as trained bees, we need healthy bees just like you need healthy dogs. What you would do is basically take the guy that doesn't know anything about bees and say on some type of criteria that that's acceptable and that's acceptable and that, but that's not. And all they have to do is have some type of threshold, and if you got lots of bees in there, they're going to be thermoregulating well and so on, and you get a good strong signature, those are acceptable ones. You can use those. Don't use the others. This is from a pesticide trial that we did this year, and you can see differences in the colonies because we had the different treatments randomized through. But it doesn't take a rocket scientist to see differences there just based on thermal images. So we're developing that for a quick rapid. We also think that, now we can bring the lights back up. We also see the people out there for the almond growers and others. These growers are rent. They pay, if they're smart, that somehow provides us a warning that the bad guy released a cloud of poison. And can you do it in less than 15 minutes? And again, I said yes. We did it in 15 seconds. We looked at a lot of things. Bees change their behaviors as they come in. Bees exposed to low-level toxins may be repelled by the garbees at the front entrance. There's all kinds of sublethal effects, but they're very difficult to capture in terms of what kind of equipment would you need, how much would it cost, how difficult it is to maintain it. And so although we use video and we saw all kinds of different things that could be used as a sign, like the dog sitting, but this bee kind of got lost coming in, or this bee got repelled, what we found that stood out more than anything was the sounds bees produce. You hit them with exposure to a really minute amount of chemical, and they sound off. And you can hear the sound. You can hear it with your own ears, and so on. What amazes is that we found out not only did that sound change occur very, very rapidly. That's where the 15 seconds to a couple minutes at max came in. But we were astonished when statistically we could group those bees into different sound patterns for different chemicals. They actually told us something about the type of chemical they were exposed to. And then the question came up, well, what happens if they're sick? You know, could you determine that? And that spun us into a USDA Small Business Initiative research project. So we first had money from the Army to look at toxic chemicals. And despite what one reporter said about us, the toxic chemicals section part of this works as good or better than the disease detection part of this does. But the disease detection and pest detection is working quite well too, thank you. And so basically, if you stress out a colony with either a chemical or a biological pathogen, it will change the sounds it produces. So here's our toxic chemicals. Now, I apologize for the graph, but these are fairly simple. If the colored dots are all a different chemical or clean air and so on, so all the purples are the same and all the oranges are the same, and if they are clustered together in 3D space, this is like a cube, the closer together, the more they resemble each other. And I think you can see that each of these chemicals sorts out to a different place in that three-dimensional space. You got a group up here that's quite different from the group over here, which is different from the group here. This one has a little overlap of these and these. So we can actually categorize and separate these things out. And we can see the differences. And you can see it yourself. They're not like all those colored dots are interspersed with each other and so on. They all segregate out into their own clumps and so on. So, foul brood. Why would a bee sick with foul brood change its sound? We assume the sounds are coming from the adult bees. And I can imagine a sick bee sounding different than a healthy bee. But presumably, if it's foul brood, the adult bees, they're there are fine. But yet the sounds change. High level of foul brood, no foul brood, moderate levels of foul brood. Varroa mites. Control, low level, medium to high. Some overlap from the medium to high. But if you're treating, the issue is don't need to treat, don't need to treat, treat. Simple as that. We not only can determine the presence, we can determine the level of infection or infestation. So the goal is, how do we apply that in your hands? First year, those plots come from the first year of the SBIR. We're on just starting our second of 2 years on what they call Phase 2. Phase 2 is aimed at producing a handheld system. We have everything from cell phone connectors to things. This is where we're really moving toward, is something like this, which is what the box scores do and stores use and so on, so that you can go in there and just run by and take a sound bite. This is the microphone. It's just a little 1/8-inch tube, a foot long with a mic here, and you just slide it in the front entrance. And you take a 30-second or up to 2 minutes, depending on what we're looking for, sound bite, and then it comes back and tells you what it thinks is going on in that hive. So imagine if you got a teenager, if you're a big beekeeper, probably not a lot of use to you if you got one hive out and back. But let's say you have 5,000 hives. And you got a teenager who has a driver's license. You can send that teenager ahead of the crews to every yard, profile the sound that all those colonies make, come home, throw it in the cradle, that night print out a printout that says, these you got to treat, these you got to look at, this has got a real problem in it, and something like that. And the crews know exactly what they need to do the next day. And they won't have to open a bunch of those hives, because every one of them that scores healthy, you can ignore. Wouldn't that save you some time and money? Now, again, these guys have to drive to these things. So the final thing is, and then, and again from our security system, there's somebody messing around with the hive, is our smart hive or pallet. This said winter 2008. This is a structural drawing. We actually have this now. And basically, we can essentially get through satellite or from cell phones, it will tell us on that pallet how all those colonies are doing. We went for a pallet because if you wire one colony, it might be an outlier. What if it dies on you or something? But if you got a whole pallet, then one doesn't do so well. You still got 3 others that are, or 4 others In our area, it's either 4 or 6 on a pallet. So you got multiple hives. That damps out some variation between the one outlier hive, and you see how they're doing. And things that we look for is that we want to weigh those colonies, because are they gaining weight, losing weight, or holding stable? If they're gaining weight like mad, you better get some equipment on them. If they're losing weight like mad, you better get out and feed them. If they're holding stable, they're okay. We have some counters. Now, we've had counters for a long time, but they were far too expensive, too many components and so on to be viable. We have a new counter now. The new counter is final testing done this spring. It's made of a printed circuit. It has no moving part. It has just a couple parts in it. And the really nice thing about it is it's going to be cheap, easy to build, and it can tell the difference between a worker bee, a queen bee, or a drone coming and going. So not only is it cheaper, but it's going to give us a lot more information. So if you're in an area where you've got a lot of pesticide problems, you can throw this thing on, and if the bees go out and don't come home, hey, you can go out and see what's going on, and so maybe grab a sample or see what the grower's doing, and so on. So basically, we've been after this for a long time as a security system for the applications we do, and as a management system for big-scale beekeepers, so that they could, in key climatic areas and so on, they could set a sentinel pallet out, and they didn't have to drive there to see what's going on, and so on. Eventually, as the technology gets better and cheaper, I mean, we've been able to do this since '95. But in '95, I had 2 486 computers in a shed with an air conditioner with cables this big around going to 10 hives. And I had to download all the data at midnight over the phones, because it took about an hour to download the data. And then I could manage my colonies in Montana. And I could actually manage them better from Montana than less experienced people could looking in the hive. But the technology wasn't there. It's taken that long for the technology to come down and get it. So this phone is far more powerful than everything I had in that. And my phone now gets email updates from my hives. Puts a new spin on call home. So that's a very brief overview of what we do. Yes, sir.